Today we'll talk about the closure properties of regular languages. Regular languages are said to be closed under the following properties, like union, intersection, difference, concatenation, clean closure, reversal, homomorphism, and right quotient. What do you mean by the term closed? Take any two regular languages and on the application of the set properties, the output or the resultant would also be in regular language. And it is true for all cases of regular languages, and therefore we call it as closed. Now we'll talk about the application of operation on the regular language. The first one is the regular language is closed under the union operation. How do I define it? Let there be two different regular expressions, R and S, which are defined, which defines the languages L and M respectively. On the union application over L and M, the regular expression will be R plus S, where plus is the R operator, and it is a combination of both, which is again a regular expression. Now, as an example, L1 is represented by AB, the whole closure, and the language L2 is represented by A plus B. Union of L1 and L2 will contain the set of all strings which are represented by L1 as well as by L2. And therefore, the new regular expression would be AB, the whole closure, plus A plus B. That is the combination of the regular expressions of L1 as well as L2 by using the OR operator plus. Next comes closure under concatenation. Here again, we'll take two different regular expressions which represent the languages respectively. How do I concatenate it? You combine the first regular expression and the second regular expression in the given order. And dot is the operator, which we don't write it explicitly, and therefore it's just a concatenation of both the strings. Therefore, L is represented by AB, the whole closure. LM is represented by A plus B. LM is represented by AB, the whole closure, concatenated with A plus B. And then comes the clean closure. Whenever to a regular expression closure is applied, it also becomes a regular expression based on the last property or the last definition in the regular expression. And therefore, if R is a regular expression which represents L, R closure will be a regular expression which represents L closure. So, or for any given regular expression, when closure is applied, the resultant regular expression is also a valid regular expression. Suppose you recall the six definitions of regular expression. The fourth rule was based on OR operator, fifth was based on concatenation, sixth was based on closure, and therefore these three properties are true for any different regular languages. And then comes closure under intersection. Before we move on to the definition, let us take an example. We have two different regular expressions which are represented by two different finite automata. Now, what are we supposed to do? We have to combine it. How do I combine it? Is you take the Cartesian product of the states of the first finite automata as well as the second finite automata. So you take the combinations of AC, AD, BC, and BD in the given order. Now, if there is a transition of 0 from A as well as a transition from 0 from C, then you will have a valid transition from AC on 0. For example, if you take here, A on 0 goes to A itself, C on 0 goes to D. So AC will move on 0 to AD. If I don't have any valid transition, then I will not represent it. Okay, so now that is how it works out. Delta of AC on 0 becomes AD. Okay, and then AC on 1, A on 1 goes to B, C on 1 goes to itself. So AC on 1 goes to BC. Similarly, A on 0 goes to A, D on 0 goes to D. So AD on 0 goes to AD, so on and so forth. So that is how you try to find the Cartesian product of the regular expression. And the regular expression, sorry, the finite automata, what you obtain, will give you an set of strings which are accepted by the finite automata 1 as well as the finite automata 2. Now we have defined the transitions from AC, AD and BC. I haven't touched upon BD even though I have drawn it. The reason is it is an inaccessible state. What is an inaccessible state? From the initial state, for a valid finite automata, you have to get connected to all these states. There may be some states which you cannot reach from the initial state either directly or indirectly. Now, if you talk about BD, from AC, I can move on 0 to AD. I can move on 1 to BC, but nowhere I can move on 0 or 1 to BD. Either through AD it's not possible or through BC it's not possible. And therefore, this BD is inaccessible. You'll never be able to reach BD from the initial state AC. And therefore, BD is an inaccessible state. You can always avoid it. Now, with this information, we'll try to understand what is given in the intersection definition. You have two different set definitions, one for M1 and the other one for M2. M2 has state Q, M2 has state P. And the alphabet alone is common because the input string has to have the same set of characters. Transitions are different, initial state is different, and the final state is different. Now, how do I find it out? If you take a state from the first M1 and the state from the second machine M2. You move on a particular string. From Qi on A, it moves to Qk. Pj on A, it moves to Pl. Now, that is two different transitions. We have combined it on a single transition. Now, having said this, how do I identify the initial state and the final state of the given intersection finite automata? The state which has the initial state of both the finite automata will act as the initial state of the resultant set. And therefore, when I have A as the initial state here, C as the initial state here, AC will act as the initial state in the resultant finite automata. Now, how do I define the final state? The final state of both the finite automata has to act as the final state here. So BC is the final state respectively. So we'll pick up the state BC, which acts as the final state of the resultant finite automata. This is how we define the intersection part. And then comes the complement. What is complement all about? Complement is about the set of all strings which are there in the universal set, but not there in the defined language L. Now, how do I define it? It's very simple. You have to find the closure. Okay, we have to find the complement of the given regular language. Now, how do I do it? The set of all final states will be the set of states which are not final in the given language. So this becomes the given input. Q0 on A, Q1, Q1 on B is Q2. Now, the second diagram, I have added a new state, which is termed as the trap state. Now, what is this trap state all about? This trap state is a state where all the invalid transitions point to. You go into the trap state and there's no way of getting out. So how do I define the trap state? Sigma is A comma B. Q0 on A is a valid transition. What is not defined from Q0? Q0 on B is not defined. And therefore, I'll have the transition of Q0 on B pointing to the trap state. Q1 has valid transitions on A as well as on B. Therefore, I will not define it. And then Q2 is the state which doesn't have any outgoing transitions, and therefore the transitions on A and B will point to the trap state. And whenever you define a trap state, it will have a self loop on all the symbols defined in sigma. So this is the DFA which you have drawn, adding the trap state to it. Now the complement of the given state. Now the complement of the given state comes over here. All these states except the final state, including the trap state, will act as final states here. So Q0, Q1 and the trap state will be the final state in the complement. Fine, that is how it has been defined. And then let's move on to let's move on to closure under difference. Based on the De Morgan's law, it says that L1 minus L2 is L1 intersection L2 complement. How do I define it? You have, whenever I take a difference, it should have the strings which are there in L1 and not in L2. So now how do I take it? We have already talked about a set of all operations, and we know the regular language is closed under complement, and therefore L2 complement is true. We also have seen that the intersection of two regular languages will also be a regular language. And based on the De Morgan's law, L1 minus L2 will be L1 intersection L2 complement, which is closed. And that is how we define a regular language which are closed under difference. Now we'll move on to the next one. So how do I define difference? We'll try to understand things. These are two different finite automata we took for intersection. Now what I have done is I have taken the complement of it. Since all valid transitions are there, no more trap state is added. C is the final state here, and I have taken D as the final state here. So this is your L2 complement. This is your L1. Now I have taken the product of L1 and L2 complement and created 4 set of states and found the intersection of it. This gives you the difference of the state languages L1 and L2. Now the next one is closure and a reversal. You have to talk about the reverse of a given regular expression. So now the reversal of regular expressions, or we'll talk about each and every operator. If A, E, and epsilon, what are these? These are the primitive regular expressions. Then the reverse of the given regular expression will be itself. For epsilon, the reversal is itself. For A, it is itself. For phi, it is itself. Now, when I have a plus operator, in general, you take the reverse of the first string and the reverse of the second string. When you have F and G concatenation, the reverse would be G's concatenation, reverse of G with reverse of F. And then the closure remains the same. You take the reverse F and you go ahead with it. Now, easy way of understanding it, if there are multiple final states, use epsilon transitions to create a single final state. And then reverse all the arrowheads, the direction of the arrowheads, make the initial the final and final the initial. So that is one way of doing it. We'll try to understand how it works and just use the JFlap tool. Now we'll go ahead with AB, the whole closure ABB. AB, the whole closure ABB can be marked in this way. I'll have A, B, and B with A comma B over here. It is A, sorry. 1 second. I'll just take it as AB, okay? And this becomes the initial state. This becomes the final state. Now, what do I have to do? I have to reverse it. So when I go in for the reversal works in this way. The initial, now this is B. 1 second, I'll make it as ABB. The reversal works in this way. The initial state, since I have a single final state, I'll keep it as such. The initial becomes the final state. The final becomes the initial state. Okay, and now you have to reverse the transitions. So instead of having a transition as B, I'll have a reverse transition from Q3 to Q2 on B. Similarly, for having a reverse transition from Q1 to Q2, I'll have transitions from Q2 to Q1 on B. And then I'll reverse the direction of transition from Q0 to Q1, which is on A. And here I'll do a modification. Since it's AB, I'll convert it to BA. So now the reverse would be BBA, BA whole closure. Fine. So that is how you try to identify the closure. And the last but one comes something termed as homomorphism. What do I do here? We do a lot of substitutions over here. And it is one application where we can directly apply it to cryptography. Maybe not today because you have a lot of complicated applications, algorithms which have come up. But earlier days to secure things, they use the concept called as homomorphism. It's just an image, homomorphic image, they call it as, which represents the given language. So what is homomorphism all about? Homomorphism is all about sigma to be A and B, and gamma is another alphabet, set of alphabet or a set of strings with B and AC, which means the homomorphic image of A, which is represented as H of A, is B, and the homomorphic image of B is AAC. And in case you have a string which has to be represented in the homomorphic form, I'll take A. In the place of A, I have to place it by B. And when I have an B, I have to place it by AAC. And other two A's, you have it as BB to be replaced. So this is how an homomorphic image comes in. This is what we call it as a homomorphism. Since just a substitution of different sequence of characters happen, at the end of the day, it is also a regular language because you have regular expressions or finite automata or regular grammar to represent with. So that is all about your homomorphism. And we'll stop here. We have one more concept called as right quotient, which we'll take it up in the next video.